Hey everyone, and welcome back to my channel. In today's video, we are going beyond just solving equations. We are diving into the brains behind the speed of the Newton-Raphson method. Have you ever wondered that why Newton-Raphson method converges so fast, or how we know it has a quadratic convergence? Well, stick around because we are going to prove the rate of convergence step by step, no shortcuts, no skipped logic, just pure math clarity. Grab your pen and paper and let's break it down together. So let's get started. We are going to let f of x is equals to 0 is given equation and x is equals to alpha be the exact root of the equation. Now we know that the general formula for NR method is xn plus 1 that is equals to xn negative of f of xn divided by f prime of xn. And by using this formula, we clearly know that the error in xn plus 1 minus alpha, alpha be our exact root and that is our approximate root. So we call it that epsilon n plus 1 is equals to the subtraction of the exact root minus the approximate root. So by rearranging the equation, we will get xn plus 1 that is equals to epsilon n plus 1 plus alpha. And similarly, we have xn that is equals to epsilon n plus alpha, same rule applied on xn. Now we are going to substitute our this and this equation back to the generic formula of nr. So it becomes epsilon n plus 1 that is plus alpha is equals to epsilon n plus alpha negative f of epsilon n plus alpha over f prime of epsilon n plus alpha. We just simply substitute in our generic formula that would be xn plus 1 that is equals to xn minus f of xn over f prime of xn. Now we are just going to simplify it. So we will cancel this with this alpha. So we are left with epsilon n plus 1 that is equals to epsilon n minus f of epsilon n plus alpha divided by f prime of epsilon n plus alpha. Now we need to just substitute back few equations at the place of epsilon n plus alpha. So for that we are going to consider Taylor's theorem. So we just simply say that since by Taylor's theorem that is x plus alpha is equals to f of alpha plus x f prime of alpha plus x square by 2 factorial and f double prime alpha plus up to so on. That is the general form of a Taylor theorem. So we are just going to specify it according to our requirements. So we are just replacing x with epsilon n and alpha remains the same. So it becomes f epsilon n plus alpha that is equals to f of alpha plus epsilon n f prime of alpha plus epsilon n square over 2 factorial and f double prime of alpha plus up to so on. Now we need its derivative also. So f prime epsilon n plus alpha, so it is equals to f prime of alpha plus epsilon n f double prime of alpha plus epsilon n square over 2 factorial, and we have f triple prime alpha plus up to so on. Now we need to substitute this and this back into our this formula. So it should be epsilon n plus 1, that is equals to epsilon n negative, and we have f of alpha plus epsilon n f prime of alpha plus epsilon n square over 2 factorial f double prime of alpha plus up to so on, divided by f prime of alpha plus epsilon n f double prime alpha plus epsilon n square over 2 factorial and f triple prime alpha plus up to so on. As we know that the epsilon n is basically the error, so we are neglecting the highest power of epsilon, because when errors multiply with each other, so it becomes more smaller, so we can easily ignore the smaller errors. So neglecting, just to make our proof easier, so neglecting the epsilon square and higher powers of epsilon, also we know that alpha is our exact root, so we need to substitute that f of alpha is equals to 0 back into this equation. So after simplification, if we look at this, we have this is the epsilon square, so we need to neglect it. Similarly, this reaches to 0 because f of alpha is equals to 0, and similarly we need to ignore this part because this is epsilon n square. So after simplification, we will get epsilon n plus 1, that is equals to epsilon n negative, we are left with just this part, so epsilon n f prime of alpha, and divided by we have f prime of alpha plus epsilon n and f double prime of alpha. Now we need to take the LCM. So after LCM, we have in the denominator the same thing, f prime of alpha plus epsilon n f double prime alpha, and here we have epsilon n, and we need to just multiply this whole term with this epsilon n, so it's become f prime of alpha plus epsilon n and f double prime of alpha, we have negative, then epsilon n f prime of alpha. Now we just need to multiply epsilon n inside and just to remove our round brackets, so it will be epsilon n f prime of alpha plus epsilon n square f double prime of alpha minus epsilon n f prime of alpha, divided by we have f prime of alpha plus epsilon n and f double prime alpha. Okay, after that we need to simplify it, and for simplification we see that this term and this term is similar, but this contain a positive sign and this contain a negative sign, so we need to just cancel this out. So after cancellation, we have epsilon n plus 1 that is equals to epsilon n square and f double prime of alpha over f prime of alpha plus epsilon n and f double prime of alpha. Now we just separate our f prime alpha. Basically, we need to take a common, and after that we need to apply the binomial theorem. So this is epsilon n plus L1 that is equals to epsilon n square f double prime of alpha over. From this part we are going to take f prime of alpha common. So here we left with 1 plus epsilon n. We have f double prime of alpha, and in the denominator part we have f prime of alpha. Because when we need to take some term common, on the other hand side, if this term is not present, then according to the mathematics rule, we need to take as a term in the numerator and in the denominator part. So that should be basically f prime of alpha plus epsilon n f double prime of alpha, and we need to multiply f prime of alpha and plus divided, and after that we are just taking a common. So this and this should be outside as a common term, and we are left 1 here and this remaining term here. After this we need to apply the binomial theorem. So for that case I am just simplify it more, f double prime of alpha over f prime of alpha. So here we have 1 over 1 plus epsilon and f double prime of alpha over f prime of alpha. Now we just shift this denominator to the numerator side and we will have epsilon n square f double prime of alpha over f prime of alpha. So here we have 1 plus epsilon and f double prime alpha over f prime of alpha and negative 1. Now we need to apply the binomial theorem. So we will have epsilon n plus 1 that is equals to, this is the same term we are writing here, and here we have, according to the binomial theorem, 1 minus epsilon n f double prime alpha over f prime of alpha plus epsilon n square, and we have f double prime alpha over f prime of alpha whole square plus up to so on. Now again we just neglect the higher powers of epsilon, so when this multiplies inside, when this multiply with this side, so we will get epsilon n square f double prime of alpha over f prime of alpha. But when this epsilon n square multiply with epsilon n square, so it becomes epsilon n cube. So we are going to neglect this. Similarly, when this multiply with this, so it becomes epsilon n fourth. So we are going to neglect this term also. So we are left with just epsilon n square f double prime of alpha over f prime of alpha. Now f epsilon n plus 1 that is equals to, I am just rearranging the terms, over f prime of alpha, and here we have epsilon n square. So I am just considering that f double prime of alpha over f prime of alpha is equals to m, and I'm going to substitute back, so it becomes m epsilon n square. So when we include the proportionality sign, so our m removes, it becomes epsilon n square. So this shows that each error is proportional to the square of the previous order. So we conclude that this method is rapidly converging method in which the error reduces rapidly. So the rate of convergence is 2, or we simply say that it converges quadratically. So I'm just writing the closing remarks. So this shows that each error is proportional to the square of the previous order. So we concluded this from this statement. This is our previous one, this is our previous one, and this is our fresh one. So we conclude that this method is rapidly convergent method in which error reduces rapidly. So rate of convergence of in our method is 2, or we simply say that because of this 2 rate that Newton's method converges quadratically. And there you have it. We have carefully walked through full proof of the Newton-Raphson method, quadratic convergence. This isn't just a theory. It explains that why this method is so efficient and widely used in scientific computing and real-world applications. So if this video helped you, don't forget to subscribe my channel, like to my videos, and if you have any questions or queries, you can discuss with me in the comment below. So thank you so much for tuning in. Take care.